So let's carry on with the next part of our lecture on work. So what is work?
Work is also a form of energy. Teacher?
No, that is incorrect. Work is not a form of energy. Work is the process where energy is transferred from one form to another through the action of a force. And a body must have energy in order to do work. So let's discuss what is work done. Work done is defined as the product of the force and the displacement in the direction of the force. And the formula is written as work by a force equals to force times displacement in the direction of the force. And the SI unit is Joule. And is defined as the work done by a force of 1 Newton, which produces a displacement of 1 meter in the direction of the force. And it is written as 1J is equals to 1 Newton times 1 meter and equals to a base unit of 1 kilogram meter square per second square. And in this case, work is also a scalar. So let's look at an example on work done by a constant force. We have a force F acting at an angle θ from the point of application and move an object in the displacement x. So to calculate work done, we can either resolve the displacement into its component. In this case, you will have x cosine θ. And by applying the formula, work done W equals to force times displacement in the direction of force, we get W equals to F times x cosine θ. In another way, we can also resolve the force into its component, and in this case, we have F cosine θ. Right, and the formula will be W equals to F cosine θ times x. So we can either resolve F into the direction of x or resolve x into the direction of F. So in the case of positive work, F and x will be in the same direction. And in the case of negative work, F and x will be in opposite directions. And if θ equals to 90 degrees, F and x are perpendicular to one another. And in this case, there is no work done. Okay, to illustrate what is positive and negative work done, we consider a woman lifting a box vertically from the floor. So in this case, positive work is done by the woman on the box, and negative work is done by the gravitational force of the earth on the box.
Teacher, I'm confused. Isn't work done a scalar quantity? Why does it have a positive and negative direction?
Yes, you are right that work done is a scalar. And this positive and negative work done is the comparison of the displacement and force, whether they are in the same direction or they are in the opposite direction. So now let's look at example 2 from your lecture note on page 5-5. In this example, we have a box being put along by John for a distance of 150 meters by a rope making an angle of 25.8 degrees with the horizontal. So by neglecting friction, find the work done if the tension in the rope is 40 Newton. And in this case, we assume that the tension is constant during the whole motion. And in this case, is the work done by the rope positive or negative work? So the solution will be work done by the tension, will be equals to, by first resolving the tension into its component. So in this case, we have work done equals to T cosine θ multiplied by x. Alright, then we will get the 40 times cosine 25.8 degrees multiplied by 150, and our answer will be 4 times 10 to the power of 3 joules. Since this work done is a positive value, work done by John is positive. So let's now look at example 3, which is on your lecture note page 5-5. This is the continuation of the example 2, and in this case we are looking at what is the work done if the rope is now parallel to the horizontal and the same tension of 40 Newton applies. So in this case, we have our theta to be 0 degree, and hence the work done will be equals to same thing, t cosine theta multiplied by x, and in this case we have 40 Newton times cosine 0 degrees multiplied by 150, and you get your answer to be 6 times 10 to the power of 3 joules. Okay, now let's look at example 4 on your lecture notes on page 5-5. In this case, we have a satellite in a circular orbit around the Earth. So first of all, we will draw the satellite and we will label the force of gravity and its direction of motion. So in this case, you will see a satellite and the force and the displacement. And you will realize that the force F is actually perpendicular to the displacement x. So to find the solution, in this case our theta will be 90 degrees and the angle between the gravitational force Fg and the displacement is this particular angle. And thus, work done by this force Fg is equals to Fg times x cosine 90 degrees. And in this case, since cosine 90 degrees is 0, you have your work done to be 0. So now, let's look at practical devices in the real-world context. Do you think all energy input is always equals to energy output?
I don't think so. For example, I put 100% effort on my physics, but I get only 60% on my grades. So my energy input is definitely not equal to my energy output.
Now I know why you get 60% output from your answer. Ideally, energy output will be equals to energy input. But practically, useful energy output is normally less than energy input. In this case, the efficiency of the device is always less than 100%. So some energy is used to overcome dissipative forces. So in this case, the dissipative forces are friction and air resistance. So based on PCE, the energy input will be equals to the energy output plus the work done against the dissipative forces. So in this case, the work done against dissipative forces is transformed into thermal energy. So mathematically, efficiency is calculated as the energy output over the energy input multiplied by 100%. And it can also be expressed in terms of useful work done over energy input multiplied by 100%. And if you divide over time, then you will have a power output over power input multiplied by 100%.
Teacher, I don't understand. How is power related to work done?
Oh, okay. We have not yet covered the definition of power until section 7 of this topic, whereby we will define power as the rate at which work is done or the rate at which energy is transferred. So in this case, we are able to use work done over time to define as the power or energy input over time to define as the power. Some examples of efficiency are that you may be asked to give some estimation of the percentage efficiency of some events, and the approximated efficiency is being listed. So in case you are being asked during examination, you are able to respond to these questions. So now let's look at example 1 from the lecture notes, page 5-3. So what must be the input of electrical power to a motor that is 75% efficient and delivers useful work at a rate of 600 watt? Can you share with me your answer?
Teacher, just now we learned power output over power input times 100% is efficiency. So in this case, we know that efficiency is 75% as given in the question. And I think the useful work, that means the power output is 600 watts. And we substitute in and we should be able to get the power input. Oh, okay. It's given 800 watts.
Great, I'm glad that you have learned a lot in this lecture. Please complete your worksheet for the simulation and go back to think about the food for thoughts. And once you have the answer, discuss with me through MSN. Thank you, class.
Thank you, teacher. Bye-bye.